Now. Okay, today we are going to do some more of the acids, bases, salts, and so on. We have 3 more lessons to finish the whole 25 lesson topic. Today we are going to look back on the stuff which we did about acids and bases. We're going to remind ourselves, you are going to be asked to write some equations. We are going to have some questions on solubility. We are going to visit Lake Natron and Magadi and somewhere else. And we're going to look at 2 big industries in Kenya, and we're going to look at some silly pictures. Okay, so we're going to start by sharing my screen of some of the stuff that we did last time. So here we go. I am going to share from here. Slideshow from here. Right, here is the pH scale. This is a little reminder. What I'm going to ask you is how come HCl acid is here on the pH scale and vinegar is here on the pH scale. What I want you to do is to think, why is HCl, which is called hydrochloric acid, obviously, why is it in a different place on the pH scale from ethanoic acid, which is vinegar? So first, I want you to have a little bit of a think. Why is hydrochloric acid a 0 and or a 1, but hydrochloric acid is often down to 0 and even negative numbers? And why is ethanoic acid only at about 3, 3.5, something like that? What is it that makes that happen? And at the other end of the scale, how come things like, well, soap, which is used to clean us quite effectively most of the time, is better for our skin than drain cleaner? What is it that drain cleaner does that soap doesn't, that makes it soap so much safer than drain cleaner? Everybody have a little bit of a think. So why is hydrochloric acid lower in the pH scale than ethanoic acid? And why would we not clean ourselves with drain cleaner, but we're okay putting soap on ourselves? So everybody have a think, and then if you want to have a go, if you want to switch on your microphone and try and tell me, that would be great. Let's see if anybody can come up with an answer. At this point, I want you always to think and then pair and then share. That you've come across this before, but it means think on your own, then share your idea, then pair, that means share your answer with your next door neighbor, and then offer your answer to the classes, because that's really important. Okay, so I'm going to stop sharing and I'm going to see if anybody has an answer. Does anybody have an answer? Why is hydrochloric acid at 0 and ethanoic acid at about 3? Why should we not wash ourselves with drain cleaner, but it's okay to wash ourselves with soap? So Mathari Mixed has an idea. Let me just pin it so I can see it properly. Because HCl, a little bit closer, please. HCl, it's slightly out of focus. Could you just get it a little bit straighter on the camera, please? It's true that it's less, has less something acid than vinegar. Has less, well, it's true, yes. It is less strong acid, but why is it a less strong acid? That's what I want to know. Why would that be a less strong acid? Don't worry if you don't know. I'm going to come to, is there anybody else who would like to switch on their microphone or write it down? Why is hydrochloric acid at 0 and ethanoic acid only at 3? Anybody got an idea? Be brave, switch on the microphone. Have a go. Oh, Dandora girls, let me just pin you so I can see it a bit better. HCl dissociates fully to give hydrogen ions, while ethanoic acid dissociates partially in water. That's excellent. That's a very, very good answer. That's a very good answer. Well done. Okay. Mathari Mixed, let me have a look, please. Just hold it still. High number for hydrogen ion. Excellent. Excellent answer. Really good. both answers. Guys, mute, please. Usharika, I'm muting you. Thank you. Okay, excellent answers. So we'll go back to the share. We haven't dealt with the soap and drain cleaner, but I'm just going to go through it again so that we can see. So the pH scale 0 to 14, strong acids at 0, weak acids higher up to 7, which is neutral. Water isn't always neutral, actually. But anyway, we're going to find some which isn't neutral in a bit. Then we have weak alkalis up to strong alkalis like drain cleaner and sodium hydroxide. Okay, so, excuse me. The way that we can check this out, even if we do not have any indicator, is that solutions containing ions can conduct electricity. And we met this last time, and I'm just going a little bit further. The idea is really simple. If a solution contains no ions at all, the bulb doesn't light. In other words, no ions, no conductivity. If we've only got a few ions, and that would be true of a weak acid or a weak alkali, we will have only a small conduction, and the bulb will light up most for something which is very, very ionized. Now, conductivity of any solution with ions does this. In other words, as concentration goes up, conductivity goes up. We don't have to worry about the labels or the units. That's not important. Until a particular point, as concentration rises, so does conductivity. Now that means the concentration of ions. That's the point. This is the concentration not of the substance in there, but the concentration of the ions. So if I've got something which is quite dilute, but is 100% ionized, then its concentration of ions will be higher than something which is concentrated, but not very dissociated or ionized. Okay. So can we explain these? HCl in water conducts easily. Just have a think. Have a little bit of a think. Why does HCl in water conduct easily? Everybody think about what you would write down. Excuse me. Why does HCl in water conduct easily? Think about what you would write down. I'm going to give you the answer in just a minute, so there's no need to share at the moment. I mean, if you want to share, that's absolutely fine, but just think about what you would write down. Church Army High School got some good ideas? Would anybody like to explain? Would anybody like to turn on their microphone? Church Army High School, would you like to speak up?
This is because the HCl almost completely dissociates to form hydrogen ions
And
chloride ions.
Excellent answer. Excellent answer. That's very good. Thank you very much, Church Army School. HCl in water conducts easily because fully giving, yes, free ions. Excellent answer, Dandora. Excellent. Well done, guys. Okay, so it's because HCl in water, we would not normally say completely ionizes, but it is certainly true that in KCSE examinations, it's okay to say completely ionizes. I would rather say almost completely ionizes, because it is never true that anything completely ionizes. Solution which contains ions do conduct electricity. Okay, and as we've just seen from the graph, more ions, more conductivity. Second question. HCl in methylbenzene or benzene does not conduct electricity. Why is that? HCl in methylbenzene does not conduct electricity. Now, some of you who can remember from last time, what I want you to do is to not just answer the question, but tell me what kind of bonding HCl has in methylbenzene. Why does HCl in methylbenzene not conduct electricity? HCl in methylbenzene. It dissolves quite well in it, really quite well. And as was said by somebody last time, methylbenzene is an organic chemical. So why does HCl in methylbenzene not conduct electricity? Either switch on your microphone, tell me that you want to have a go at the answer, or show me it on the screen, please. You're doing very well today, students, really very well.
Church
Anybody go?
Army.
Yeah, go. Church Army, have another go.
So this is because HCl does not dissociate fully in methylbenzene.
I'd like you just to refine that answer a little bit. I want you to think, if it's a very good answer, but it's not about it fully dissociating. Just think about it. If it doesn't conduct electricity, full stop. Anybody? If HCl does not conduct at all when it's dissolved in methylbenzene. Anybody? It's very nearly Church Army School. It's very good. Okay, if it doesn't conduct at all, then it must be this. It does not produce any ions. In other words, we're used to HCl being H plus Cl minus, but it's not. HCl is a covalent molecule unless there is water present or some other aqueous solution. So HCl in water, whoops, sorry, it says in water. my error. I wrote water there. I meant methylbenzene, obviously. This shows that HCl in methylbenzene does not produce any ions. Unlike in water, it doesn't produce any. In the non-polar solvent of methylbenzene, it is covalent. Here's another question. CH3COOH, that's ethanoic acid, only conducts a little in water, even if it is very concentrated. So if I take vinegar that we normally would put on food or whatever, or use to preserve food, that's quite dilute. But even if I make it very concentrated, it only conducts a little bit. Who has an answer to that? Why? Can you explain that? Ethanoic acid only conducts a little bit, even if we've got a lot of molecules of ethanoic acid in our water.
It partially dissociates in water to form less ions.
It does, and therefore there are only a very few ions. Well done, Dandora girls. Well done, Church Army School. Who is the speaker? Church Army, who is your speaker?
Job Flavian.
Say again, sorry.
Job Flavian.
That's fantastic. You have a very clear speaking voice as well. Perhaps you should read the news. And Dandora girls will write it for you, and then you can speak it. Okay. Last question. We came across all these last time. It's just reminding you. Okay. So the acid is weak, which means that it doesn't matter how many molecules there are. Very few of them dissociate or ionize, so there will be very few ions. And if there are very few ions, even if it's concentrated, it can't conduct very well. So the last one, and it should really have said sodium hydroxide and calcium hydroxide are both bases, are both alkaline. They're both alkaline, but why does sodium hydroxide conduct much better than calcium hydroxide when calcium hydroxide has two hydroxides? So you might think sodium hydroxide, NaOH, would be not as good as CaOH twice, because what makes an alkali, if you remember from last time, is the presence of OH minus ions. So have a think. NaOH conducts much better than Ca OH2. Yes, very good, Dandora. The last two parts of your sentence should be swapped over. The dissociate and strong base should be swapped over. In other words, you should say it fully dissociates and therefore it's a strong base. But otherwise, that's an excellent answer. Well done. Yes, the answer, ladies and gentlemen, is sodium hydroxide is a much stronger alkali. Now, I want you to get used to this idea. Bases are a large number of chemicals which react with acids, which neutralize acids. But those which are soluble are called alkalis. And that's really rather important. So when we're talking about something like sodium hydroxide and calcium hydroxide, if they are AQ, that means they dissolve in water, even if not very well. And that means they are alkalis, not just bases. So we should try and use the word alkali if it's soluble. So NaOH, much stronger alkali than CaOH twice, calcium hydroxide, which means that NaOH will ionize much more, which means there are many more ions. You could be specific. You could say Ca2 plus and OH minus ions than NaOH, so it conducts more. Very good answers. Well done. I'm really impressed. Good. Okay, moving on. So then we did some equations. I'm just going to show you them very briefly just to remind you. We said, oh yeah, if we start to write an equation and we remember how to produce ionic equations, these dissociate, AQs dissociate always. So HCl becomes H plus Cl minus, NaOH, Na plus, OH minus, and so on. And that means that we can then do the cancelling. The Cl minus from one side and the other side can go. The Na plus can go from both sides. And therefore, it simplifies to the ionic equation H plus OH minus goes to H2O. Then we came across some other equations. I put the state symbols in, and I said sometimes in KCSE, they ask you to predict what you would see. Can anybody remember what I said we should try and remember when we look at an equation? Here are some equations, and if we're looking for what we can see, then apart from a color change, I said there was one other thing we should look for in an equation with the state symbols. It helps me say what is going to be happening here. So in C, it's not there in C, but I should know that copper sulfate is blue, and therefore this is going to go blue. I might know that copper oxide is black, so black goes blue. What physical state am I interested in seeing? In these, what am I looking for if it says what I would observe? Anybody tell me? If you look at the equations, there they are. What is it that you are looking for if you are looking for an observation? I'll tell you in just a minute if you can't think. Anybody think? Okay, it's gas. If you see in this first one, we've got CO2G. In the second one, CO2G. In the third one, no G. In the fourth one, H2G. And the fifth one, CO2G. Now, the G means that it's a gas, and we are taking, if we look at all of them, they are all solids being added to a solution, and we will always assume that the solutions are colorless. And don't worry about whether these other chemicals are colorless. We are going to see fizzing or effervescence or bubbles. It doesn't matter what you say. It's about what you, if they say observe, it means what would you actually see. Okay? So you're looking for gas, which can tell you what you are going to see. All right. Then here are some general reactions of acids. With reactive metals, with a metal oxide or a hydroxide, and with a metal carbonate or hydrogen carbonate. So I'm going to give you a chance to just see if you can balance these equations. So in the first one, I would like you to use zinc and hydrochloric acid. So in the first one, it's zinc and hydrochloric acid. In the second one, it's copper oxide and sulfuric acid. And in the third one, it's calcium carbonate and hydrochloric acid. I'll stop sharing. I'll write it on the what's it behind me. So it's going to be, hello. The first one is Zn and HCl. That's the first one. I hope you can see that okay. Not that great. I'll just change colour. Hang on. I hope this will be better. In the second one, it's copper oxide and sulfuric acid. And in the third one, it's calcium carbonate and hydrochloric acid. Now, these are the three classic reactions: acid plus metal, acid plus base, oxide or hydroxide, and acid plus carbonate or hydrogen carbonate. Just have a go, see if you can balance those equations. So there they are. Just see if you can have a go. Have a go at all three before you show me. Just see if you know the general equations. Because an acid and a metal always produce two chemicals. Acid and a base, two chemicals. Acid and a carbonate, three chemicals. And you may want to write down the general equations in a minute. Wow, some Dandora girls very fast. Let's have a look. And very, very nearly. There's just one error in your third one, Dandora. Mathari, hang on. Let me just pin you because your camera isn't very clear. Let me just have a quick look. Hang on. Excellent. Well done, Mathari Mix. That's very good. Let me just get rid of that. Hang on, Dandora, just coming to you. Yep. Very good. Well done. Very, very good. Kabiro, can I have a look? Show me. Kabiro? Oh, you've paused. Up a bit, please. Up a little bit more, please. Zn, very nearly, but it's got to have it. Hydrogen goes around in pairs. That's H2, and Zn is zinc chloride is ZnCl2. ZnCl2. Okay, ZnCl2. Okay, I'm going to come away and I'm going to share my screen now. So here we go. Whoops, that's not what I want. Come on. Okay. Let me just get rid of this. Well done, Mathari. Very, very good. Yes, well done. Okay. Okay, here we are. Oh, come on. For some reason, my camera is not behaving itself. Why is this happening? Okay. So I hope you can see this okay. So the first thing is that Zn and HCl, this is a metal and acid makes a salt and hydrogen. That's the first thing to remember. If you can remember general equations, acid plus metal, salt plus hydrogen. In acid plus base, we get a salt again, only this time we have water, because instead of hydrogen being replaced by the zinc, we have an oxygen, which is going to go with this hydrogen. So in this first one, we get zinc chloride, but you have to know that zinc has a valency of 2. That means because chlorine has a valency of only one bond, it will be ZnCl2. And hydrogen exists as a diatomic molecule, two atoms joined together. That means now I have to balance it with 2 HCl. It will be solid, aqueous, gas. In this one here, CuO, H2SO4 turns into its copper sulfate, which many of you will know, and water, and that's it balanced, just really simple. In this one, the carbonate or hydrogen carbonate, sometimes called bicarbonate, and acid always makes a salt and water and carbon dioxide. And therefore, Ca goes with the Cl, so it's going to be Ca in group 2, so valency of 2, chlorine group 7, so valency of 1, so it's CaCl2, and water and carbon dioxide. If I look back at this, the only thing which I need to do is to have 2 HCl, and that's it. Okay. All right. So back to sharing my screen. Here they are. Zn plus 2 HCl, ZnCl2, H2, CuO, H2SO4, CuSO4, H2, and CaCO3, 2 HCl, CaCl2, H2O, CO2. All right. Now, the next bit was about solubility curves, and we looked at them last time. I said this was quite a useful table to know about. I think it's one of those tables that some of you will remember very easily, some of you will not remember very easily, but it is a very useful table to have, I think. Then we came across some solubility curves, and we came up with some conclusions, which were some salts are much more soluble than others. In general anyway, they become more soluble as temperature increases. That is true of solids, not of gases. Gases in general become less soluble. And number 3 is usually the measurements are in grams per 100 grams of water. Then above the line, some of the solid cannot dissolve. On the line, it is just the maximum amount that can dissolve. And then in the below it is just a solution. And then we can find the solubility of a solid by just drawing the line up until it hits from temperature upwards. Okay, so here we are. Okay, now this was one that I showed you. It's very simple. Hang on, something has gone wrong here. Where is everybody? This was one that I showed you very simply. It showed you how to find the solubility at a particular temperature. It was really easy. And then we said, okay, there's 90. Then how we do another kind of question is this. Here was the question. If a student had 50 cubic centimeters of the solution at 50, how much KNO3 would be precipitated if it was cooled to 20? Have a quick look at it yourself now. You may be able to remember the answer, but just have a quick look at the graph and see if you can do it. So student has it at 50, and then it's cooled down to 20, and they've got 50 cubic centimeters of it. What will happen? Well, here's how the person would start by doing it. Firstly, I said in an exam, try to highlight, try to remember exactly what is in the question. So there's the solubility in grams per 100 grams at 50 and at 20. So the person who was answering this said 90 minus 34 is 56. And I said, but it's a bit of a tricky question. Can you remember what the problem was? Can you remember what the problem was? So in other words, if you look at it, the question says they've got 50 cubic centimeters at 50, and it cools down to 20. Because at 50 more dissolves than at 20. So at 50, 90 dissolves, but at 20 only sort of 34 dissolves. And what we said was it looks like the answer is going to be 56, but the answer was actually 28. And it was 28 because we only had half the volume. Okay, half the volume. Okay. So there are some other things which you need to know about in this part of the specification, this part of the syllabus. The first thing is you need to know about the solubility curves of NaCl, KClO3, CaSO4 and Na2CO3. You do not have to remember them, you just have to understand some bits about it. Then you have to know about fractional crystallization, then about trona and sodium carbonate and salt, and then we will basically be stopped. Okay, so what I'm going to do is I'm going to show you the graphs so you can see how they vary. And here I've got one which is the solubility of salt, but I'm comparing it with potassium nitrate. And why I'm doing this is because we could get a graph of sodium chloride which makes it look like the potassium nitrate line if we expanded the y-axis. Look at sodium chloride. It really doesn't vary very much with temperature, whereas potassium nitrate is less soluble with sodium than sodium chloride at low temperatures until about 24, and then much more soluble. That's very important to realize. Sodium chloride does not change in solubility very much. This is potassium chlorate, KClO3, potassium chlorate 5. It is a very similar sort of line to the potassium nitrate. You don't have to remember it, I just want you to look at it and recognize it. So we would be able to find any solubility. There's 80 up to there and across, and I would read it off and it would be 38 or so. Here's calcium sulfate. Now, calcium sulfate can have several different lines. What is important about calcium sulfate is that it becomes less soluble as we heat it up. Less soluble. Now, the reason we've got several different lines is because we have different types of calcium sulfate. This is one with half a water of crystallization. This is anhydrous. This is 2 waters. And there are waters of crystallization up to 7. But here, the point about this is that calcium sulfate becomes less soluble. Here's sodium carbonate. Sodium carbonate is a mixture of the other 2 types of graph. So sodium carbonate seems to increase in solubility up to around about 40 degrees, and then it drops. Oh, this is a French one, look. Solubilité aqueuse. My French is fantastic. So there, that bit is like the potassium nitrate, and then it's dropping like the calcium sulfate. Okay, that's an unusual thing. That's an unusual graph, but it's very important you know it. So let's go back and just check we know them. Okay, so sodium chloride, not much change. Potassium chlorate, what we expect. Calcium sulfate, the opposite to what we expect. And sodium carbonate increases and then decreases. Now, this is about fractional crystallization. You've heard of fractional distillation, which is the way that organic oils are separated. And this is about fractional crystallization. It's about separating solids. And here's a question that was in KCSE, and it says, how could you separate 40 grams of sodium chloride from 150 grams of potassium nitrate? In other words, if you started with 150 grams of potassium nitrate and 40 grams of sodium chloride, what could you do to start separating them? Well, what we do is this. We go, okay, let's have a look at this graph. Here is 150 grams of potassium nitrate. So I've got 150 grams there in 100 grams of water. And I find that that dissolves at about, I don't know, 77 degrees Celsius. Okay. If I look at sodium chloride 40 grams, it's about the same sort of temperature. In other words, at about whatever that is, 76, 77 degrees Celsius, if I have 100 grams of water, I could dissolve 150 grams of potassium nitrate, but only 40 of sodium chloride. So what I would do is to get 100 grams of water, 100 mils, 100 cubic centimeters of water. And I would add this mixture, because we assume that it is actually a mixture of solids, and I would heat it up to around about 80 degrees. Okay, and at about 80 degrees, both the potassium nitrate and the sodium chloride would dissolve. And then I would let it cool down. And as it cools down, the potassium nitrate stays in solution. The sodium chloride stays in solution because it is soluble at lower temperatures, mostly soluble because it's just about straight across. Whereas the potassium nitrate, it drops really fast. That means that the potassium nitrate is going to come out of solution. I will see crystals forming. Now, some of the crystals will be sodium chloride, but hardly any of them. And this is how it works. So in other words, I take my water, I heat it up, I let them both dissolve, and then because the potassium nitrate drops much, much faster in its solubility, I let it cool down. And as it cools down, more and more of the potassium nitrate comes out, more and more, until I get down a little bit further, probably down to this sort of temperature. So in other words, I would be able to let it crystallize for a while, let it cool down for a bit, and then I could filter it, and almost all of the crystals which are in there would be potassium nitrate and almost none of sodium chloride. So in other words, you would always be given a graph like this where one not very soluble, one very soluble, and therefore I would be able to get my potassium nitrate out. And that's the basis of something that happens here. Now, this is about Trona. You may have come across Trona. Trona is sometimes available in washing powders and things like that. You may have come across it in bottles. You can buy it as Trona. Somebody told me that Trona comes from Lake Natron or Natron. It does not. I'm going to show you a stupid picture. I was looking for a picture of Lake Natron. Natron is in Tanzania, almost all in Tanzania, just off the southern border with Kenya. And I found this picture. It's really stupid. This picture is this guy is trying to sell us that it is the nastiest lake in the world, and he is suggesting that it dissolves him or something. That is ridiculous. It does not. It is true that animals which die in this lake do end up a little bit weird. Here is the lake. It's got a volcano behind it which feeds it with warm water, and we've got flamingos. If the flamingos die, something odd happens to them. They get coated with salt because the water evaporates and the salt is left on them, which is really quite weird. But let's go to Kenya. So let's go a little bit south of Nairobi and let's go down to Tata, which is the Indian company. And let's go down to the soda company here. And this is a much nicer lake. Here it is. Much nicer. Really much nicer. And it has flamingos too. But it has something else. And that is that it has this. Now, this is where different levels of salt are being precipitated out. It is a landlocked lake, and that means that the salts dissolve into it, they rush in off the streams and so on, and then the water evaporates, and we are left with solids. It's a rather good picture, isn't it? But on the lake, we have this. Now, this is basically an engine which drives these buckets, pulls them along. And these are used to roll and to compress and collect a particular chemical. And the chemical dissolves like this. Now, this is its solubility curve. And if you were watching a few moments ago, you may remember which one of them dissolves like has a solubility curve like this, increases and then decreases. Okay. And this is what it is. It's natron or natron. And natron is a weird chemical. So here's a question. Would you collect it in the day or in the night? Now look at the solubility. The solubility is quite low at a low temperature, and it increases steeply, okay? Increases steeply until a maximum at around about 38 or so degrees, 37 degrees Celsius, and then it drops off. So would you collect it in the night or the day? Well, look at this. As it cools down at night, you might assume it's going to cool down at night. It's going to come out of solution more. Okay. Here is the soda company run by Tata. It looks like this. It is an extraordinary set of buildings on the lake. And the lake is, some people complain about this because it is not pretty to look at, but it produces a very large amount of natron. So, of trona, sorry. So here we are. This is what it is. It's what we call a double salt. It is sodium hydrogen carbonate and sodium carbonate. You need to know this. Sodium carbonate and sodium hydrogen carbonate. Now I'm going to stop sharing just for a minute so I can show you what that means in practice. So I'm going to just change to my other screen. So it is a mixture of sodium carbonate and sodium hydrogen carbonate. It's what we call a double salt. A double salt, the two salts behave as though they are completely separate, okay? So that if there was something that sodium carbonate did and sodium bicarbonate or hydrogen carbonate didn't do, then this would behave, even though they're mixed up, this would behave on its own. But what we do is we tend to write an equation, a formula, like we have added them together. So we go, okay, it's Na3H, and then we put the carbonates separately. So we see I've got two carbonates. So this is what it is. It's called sodium sesquicarbonate or trona. This is what it is. So it's 3 sodiums, 2 from there, 1 from here, 1 hydrogen, and 2 carbonates. And that's the chemical which they're trying to dredge out of the lake, well, trying to evaporate the lake to get. And you need to know that. You need to be able to write that and without any trouble. So now I'm going to go back, and if my camera gets out of the way. Come on. Okay. So here's Trona, NaHCO3, Na2CO3 combines to get Na3HCO3 twice, and it normally has two waters with it, two waters attached to it. And what happens is that they take it, they evaporate the water a bit, they try to evaporate the water a bit, and then they concentrate it, they dry it, they do something called calcining. You don't need to worry about that. And then it's heated. And this is what you need to know next. That when you write the equation, you need to start with two of these, of the Trona formulas, okay? So 2 Na2CO3, NaHCO3, 2H2O, or 2 Na3HCO3 twice 2H2O, okay? Doesn't matter which one you use, whether you join them together or not. And when they're heated, they make 3 sodium carbonates. 3 sodium carbonates, okay? And a carbon dioxide and 5 waters. Now, this is an equation worth being very aware of because they often ask questions about it. The idea of getting the Trona out of the lake is to produce what we call soda lime. So Na2CO3 is washing soda. It is very powerful. It's very alkaline, which is why the lake is quite alkaline. The lake has a pH of about 10.3, I think it is, which is very alkaline. It would feel like soap. It would feel slippery on you, but that's the equation. So they are trying to produce Na2CO3. Na2CO3 is used in many processes, many processes. Okay, so washing soda, it's used in washing powders and so on. Let's have a look, see what they're used in. It's used in making paper. It's used in soaps and detergents. It's used in treating water. And normally they will ask you for 2 uses. Okay, so perhaps the purification of pulp into paper and making detergents because it's used in making washing powder and so on. Okay, so that's the use of sodium carbonate. Okay. And the second place we're going to go on our little journey today across Kenya is to go just north of Malindi on the way up to Lamu. And this is very famous internationally because this is a place where we look at the line here with the black triangles. This is where we get sodium chloride out of the sea. Now, because it doesn't vary much in temperature, we can't simply cool it down or heat it up to get it out of solution. So look at sodium nitrate. Sodium nitrate, very steep line. If I took it at 90 and cooled it down, I would get an awful lot of the solid out, but just cooling down salty water does almost nothing to it. So what we have to do is something different. What we have to do is this. We have to trap it in lagoons and then spoon it up so the water will evaporate. Okay, that's the important thing. So the water will evaporate. So in other words, we can't do it simply by cooling or heating. We can't have a fractional crystallization for it. It won't work. All right, that's very important. It's made in huge quantities, really huge quantities. It is one of the large producers of salt in the world. And why do we want to use salt? We want to use salt because we want to make sodium and chlorine and sodium hydroxide and many other chemicals from sodium chloride. Okay, so let's go back. Trona, Na3HCO3 twice, CO3 in brackets 2, 2H2O. Write the equation using 2 of them and producing 3 Na2CO3s and carbon dioxide and 5 waters. Salt doesn't change its solubility with temperature very much at all, so we can't just heat it up or cool it down and it will come out of solution. we have to actually evaporate the water and then pile it up. And we do that because we want to do this to it. And this is the electrolysis. And the electrolysis of molten sodium chloride, which we have to know about. Okay. All right. Okay. So that, whoops. Am I back? Yes. Good. Excellent. So that's basically the end of that part of this. Oh, hello. Sorry, something weird happened to my screen then. That's basically the end of this part of the specification of the syllabus. So let me just show you where we've gone. Oh, come on. Right, here we are. So if you remember right at the beginning of this topic, I showed you, I said, oh yeah, look, here's the syllabus. It is absolutely huge. It makes you go, oh no, there's too much of it. It's really, really big. But I said we were going to cover these bits. And so we have so far. So we have covered the acids and bases, weak and strong. We've covered some salts as being ionic compounds. We're going to do something else on those in just a minute. We're going to do precipitation reactions using ionic equations. And then we have done about the solubility with temperature, solubility curves, fractional crystallization, and extraction of sodium carbonate and sodium chloride. Okay, so that's what we've done. Now what we're going to do is we're going to do, using my other board, we're going to write some ionic equations. And this is where I'm going to get you to do some work. And hopefully, here we go. Okay. So we're going to do a little bit of practice writing equations, turning them into ionic equations, and spotting what would happen, what we would observe, okay? So what I'm going to do is I'm going to write part of an equation. You're going to turn it into a full equation. Then you're going to try and turn it into an ionic equation and tell me what you would see, okay? So here we go. In the first one, I'm going to start with HCl, which is an acid and therefore is AQ. And I'm going to add to it, perhaps in a titration, NaOH AQ. What I want you to do is to complete the equation. Then I want you to turn it into an ionic equation and then tell me if you would be able to see anything. Okay, that's the first one. I'm going to write a few down so that you can, those of you who are a little bit quicker can carry on. In the second one, I have nitric acid. I'll come to you in just a minute if you're saying you can't see this. And sodium carbonate. And in the third one, okay. So I'm going to give you a few moments to try and balance those, then turn them into ionic equations. What is important to know is that I am saying that everything that can be soluble is. In other words, the salts will be soluble, okay? Now, I know it's not entirely true about one of these, but that's okay. All right, so just try and write the equation. Equations. When you think you have an idea, just you can always show me, but just take a moment to have a go and do them completely.
Excuse me, sir. Sodium carbonate. Sodium has a 2. Yeah.
Oh, la 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 la. Okay. Sodium carbonate, which we've come across a couple of times today. Sodium is in group 1. Carbonate has a valency of 2. Na2CO3. Are there any other errors? Any other errors? Is this right? Is this nitric acid? Is that sodium hydroxide? Two points to Dandora. Very, very nearly. In the third one, it is not hydrogen. And in the second one, could you just show me that again, please, Dandora? It's not hydrogen, it's H+4COS. That's better. And in, yes, and in the second one you have done, yes, you have balanced. Well done. Church Army, hang on, I'm just going to have a look. Let me just unpin that one. HL, yes, excellent. Well done. Very, very good. Well done. Church Army High School, school. Very good. Well done. That's the chief balancer of equations for today. I'm just going to look at Mathari. Everybody should be having a go, because then you have to try and turn it into an ionic equation. Hang on, Mathari, I'm just coming to you. Just come in. Okay, show me. Anyway, very good. HNO3. Hang on. Hold still, please. Could you come a little bit closer, please? Just a little bit closer. It's not very well. It's not very in focus. Let me just see if I can make it bigger. I can't quite read it. Your camera is a little bit fuzzy. I'm really sorry, Mathari, because the first one is right, but your other ones, like it's a little bit fuzzy, if you know what I mean. Okay, because I need to get on, so I want to go on with this. So the first one is an example of an acid and base. So acid and base, salt and water. So it's going to be the sodium with the chloride and the hydrogen with the hydroxide, H2O. Now, I said the salts are all AQ, they're all soluble. So then what we have to do is to split these. You may remember this if you were here last time. All the AQs can be split, okay? But solid, liquid or gas cannot be split. So water has to stay as it is. So we're going to have water at the end. So this is going to split into H plus and Cl minus. and Na plus and OH minus, and that's going to make Na plus and Cl minus and water. And then we can do the cancelling. I've got a chloride here and a chloride here. I've got a sodium ion here and a sodium ion here, and therefore H plus OH minus H2O is the ionic equation. Simple. I'll just get that out of the way. Second one. Again, they split up. I'll write it up here. This one, AQ, splits into H plus and NO3 minus. This is going to split into 2 Na plus and CO3 2 minus. And this is going to turn into sodium nitrate, NaNO3. Acid plus carbonate makes salt and water and carbon dioxide. So I've got water and carbon dioxide. And at this point, I go, wait a minute, I've got 2 sodiums here. So I need 2 there. And that means I need 2 of these. And that means here I have 2 of those and 2 of those. And this is going to go on to make, this is going to split up. This is going to be AQ. So it's going to make 2 Na plus and 2 NO3 minus. And water is a liquid, carbon dioxide is a gas. They cannot split up. And so it's water and carbon dioxide. Now, if I look at this, I've got carbonate on this side, but not on that side. So I can't get rid of that. I have 2 sodiums here, and I have 2 sodiums there, so I can get rid of those. That's okay. I also have 2 nitrates here and 2 nitrates here, and that's it. So I'll just rewrite that up here. 2H plus the carbonate anion makes water and carbon dioxide. Does it balance? Always worth just checking afterwards. 2 hydrogens over here, 2 hydrogens there, 3 oxygens here, 1, 2, 3 there, 1 carbon, and the charges should balance as well. So 2 pluses, 2 minuses, no charges, that's okay. The last one, until we do the last thing, there's one other thing I want to get done, so I'll just move this up. H2SO4 and calcium hydroxide, acid and base, salt, calcium sulfate, and water. Balance it, 2 hydrogens here, 2 hydroxides here, 2 waters there. I said the salt was AQ, so that's AQ, that's liquid. This will split, it's AQ, that's AQ. This will split into 2H plus and SO4 2 minus. This will split into Ca2 plus and 2OH minus. This will split into Ca2 plus and SO4 2 minus. And the 2 waters will not split up. I hope you can see all of that. Then I can say, look, I've got a sulfate here, a sulfate here, I've got a calcium here, I've got a calcium here. So it's 2H plus 2OH minus goes to 2H2O, or I could get rid of the 2's and turn it into H plus AQ plus OH minus AQ goes to H2O liquid. Now, the last thing I want to leave you with is a precipitation reaction. And I want to look at that. And this is one which is used as a test for a halide. You need to know, for paper 3 particularly, you need to know tests for things like halide and sulfate and so on. And it goes like this. If I want to test for a halide, I use silver nitrate. Silver nitrate dissolves in water. If I add a a solution to it which contains a halide, and in this case I'm going to take bromide. If I add KBr, and it dissolves in water, so I'm going to have that. So I'm going to take my silver nitrate, I'm going to add it to my potassium bromide, and I get silver bromide. But silver bromide is a solid, and that's really rather important, because that's the test for the halide. I get a precipitate, it's a creamy coloured precipitate. That's how I know that I've got bromide here. And I then also have the other two. So it's what we call, I'm sure you know, a double decomposition, swapping over the ions. So the potassium and the nitrate are going to get together. Sorry, I'm going to put it down here. AQ. So the AQ split just like in the last thing. So I'm going to get Ag plus and NO3 minus and K plus and Br minus goes to AgR. AgBr, because it's solid, it doesn't split up. And K plus and NO3 minus. Let me just move that out of the way. So this is how it ends up. So now I've got a nitrate here and a potassium that I have over here, and therefore this is the precipitation reaction. Here's one for you to do. So this is what happens. The silver nitrate and the bromide, the potassium bromide, makes a precipitate which we can see, and therefore we know that the bromide is present. The important thing about this is that what's really happening is that the nitrate and the potassium take no part in it, because when it's dissolved, they are completely separate. So the ions are what we call spectator ions. They're just watching. So here's one for you. The last thing today. So the way that we test for a sulfate is using barium chloride. And I'm going to add a sulfate to it. I'm going to tell you that barium sulfate is very insoluble. So what I want you to do is to complete this equation, turn it into an ionic equation, and see if you can see what the whole ionic equation is going to be. Just have a go at that. Anybody got the answer? That's really good, Dandora. Really, really well done. Brilliant. Well done. Mathari Mix, let's hope your camera is good. Yes. Okay. Well done, Mathari Mix. Church Army, come on, get up to the camera. Indeed it is. Well done. Okay. So I think everybody's got it. So it becomes the BaCl2 splits into Ba2 plus and 2Cl minus. Here, Ba2 plus 2Cl minus 2Na plus.
Excuse me, sir.
Yes.
Sodium has a 2.
What?
Sodium has a 2 in the first equation.
Well done. 2Na plus SO4 2 minus goes to BaSO4, not split up, and the rest of the molecule will be the sodium chloride 2NaCl. This therefore will be barium sulfate, not split up, but 2NaCl will be 2Na plus and 2Cl minus. The Na and Cl ions are the same on both sides, and therefore we have Ba2 plus Aq plus SO4 2 minus Aq makes BaSO4 solid. Okay. All right. We have finished. Let me just change my camera. Okay. Thank you very much for your patience. I'm sorry we're a couple of minutes over. 3 minutes over. Oh, no. Well done. And really, congratulations. Next time we will be doing amphoteric behavior and so on. But I also hope that next week I have to find out whether I can get in on a different day. But I'm hoping I will be in a laboratory and show you some acid reactions, some proper chemical reactions in a laboratory. Some juju, as we used to call it. Okay, but for the moment, I will say goodbye and thank you very much indeed for your attention and your hard work. You really are very, very good students indeed. Goodbye.
Bye, Mr. Snell. See you later.
See you later, sir. Yeah, see you later.
Bye-bye.
Bye-bye now.
Bye, Dandora. Bye, Church Army.
Bye, Matari. Bye-bye, Dandora. I'm stopping recording